Thank you all for coming to my talk. My name is John Light. I work for a company called Alpin Labs, and today we're going to be talking about Bitcoin rollups 101. This is for a talk for complete beginners, people who aren't familiar with Bitcoin rollups, but just curious to learn the basics. So we'll start off by asking, what is a rollup? No, not those rollups. We're talking about Bitcoin rollups. So a rollup is a blockchain that stores enough data inside the blocks of a parent blockchain to be able to compute its current canonical state. And we're going to talk later about why that's actually important. But this is the simplest kind of explanation of what a rollup is. And so a Bitcoin rollup then is a rollup which uses Bitcoin as its parent chain. This is a very simple high-level diagram of what a rollup looks like. We've got the rollup blockchain on top running parallel to the Bitcoin blockchain. Periodically, the rollup blockchain will take its block or state data and then just stick it in a Bitcoin transaction, get that transaction confirmed in a Bitcoin block, and now the rollup state data is stored in Bitcoin. So this kind of architecture gives rollups a couple of different properties. One is that rollups have data availability guarantees that are equivalent to their parent chain. This is relatively easy to see because we are actually storing the rollup state data in Bitcoin blocks. We know for sure that the rollup state data has the same level of availability as Bitcoin block data, or I should say any other Bitcoin block data that like archival Bitcoin nodes have to keep around. Another quality that rollups have is that they have double spend security equivalent to their parent chain. This one is a little bit less intuitive, but if we add some labels to the diagram, then we can see that if we wanted to reorg rollup block 1 after it has been confirmed in Bitcoin block 1, then we would actually have to reorg rollup block 2 as well as Bitcoin block 1 and Bitcoin block 2. Because just like any other Bitcoin transaction that was confirmed in block 1, if we reorg block 1, we invalidate block 2, and we have to rebuild that block as well. So therefore, any rollup transactions that were confirmed in rollup block 1 and therefore Bitcoin block 1 have the same level of double spend security as every other Bitcoin transaction that was confirmed in Bitcoin block 1. So there are multiple different kinds of varieties, so let's talk about the different varieties of rollups. At the high level category, when you're thinking of this ontologically, we have sovereign rollups, and sovereign rollups are a kind of rollup where the canonical chain is defined by end-user full nodes rather than a canonical bridge smart contract, which we'll talk about later. Therefore, these types of rollups can hard fork without breaking any canonical bridge, which gives them this name sovereign rollups. They are sovereign from the control of any other network. They can change their rules kind of at will without worrying about breaking anything external. Again, we can see how this works if we label the diagram. At block R, the rollup has the gray set of rules, and then at block R1, there's a hard fork, and the full nodes on the rollup network begin to respecting a different set of consensus rules, and so the blocks are now blue, and they just look for blocks that conform to their rules that have been put into Bitcoin. And they can pretty easily just transition from one set of consensus rules to the next, again, without breaking anything external to the rollup. Now, on the other hand, we have smart contract rollups. And so a smart contract rollup does have a canonical smart contract bridge that is connected to their parent chain. This bridge contract knows the rollup consensus rules, which enables it to fully verify the rollup state transitions. This is what actually enables the bridge to be secure. And so the bridge contract is actually the final arbiter of what is or is not a valid rollup state transition. Therefore, a smart contract rollup cannot hard fork without breaking the bridge. And so if we look at a similar diagram again, now we've got this contract on Bitcoin that is verifying the rollup state transitions. It also enables Bitcoin to travel back and forth between Bitcoin blockchain and the rollup blockchain. And if at R2, the rollup full nodes change their consensus rules in a way that is backwards incompatible, so a hard fork, then the contract will actually just reject this state transition because it doesn't conform to the rules that were encoded in the contract, and any attempts to take Bitcoin out of the smart contract according to those new rules, it's going to fail. And so the nodes that switched over to the blue rules have effectively been forked off the rollup network, and their state transitions are not going to be respected by the bridge smart contract. So let's enhance. Look closer. Take a closer look at this. So within the category of rollups, we also have optimistic rollups. And these are rollups where the nodes will optimistically accept state transitions as valid. And if a state transition is invalid, then anyone can broadcast a fault proof that proves that the state transition is invalid. And if a state transition is proven to be invalid, then it will be rolled back, and the rollup chain will proceed from the end of the last state transition. So again, going back to the diagram, we now have a label for the actual state of the rollup. And we also have this new box that's shown up called the challenger node. And what the challenger node is going to do is it's actually going to watch the state transitions that the rollup block producer is putting into Bitcoin. And if the state transition is invalid, then it's going to put a proof into the rollup smart contract on Bitcoin, which cancels the state transition. And now the next state transition for the rollup has to refer to the previous valid state transition before the invalid state transition was attempted. Now we also have pessimistic rollups. As you can guess, these are rollups where the rollup nodes pessimistically perform full validation of each state transition. So invalid state transitions are caught immediately and then rejected. Let's take a closer look. Within the pessimistic rollup category, we have re-execution rollups. These are rollups where the nodes will actually just re-execute all of the transactions in each rollup state transition to determine the validity of the state transition. And as a consequence, we need to have the full transaction data stored in to be included with each rollup block. This really only makes sense in the sovereign rollup context. And this is a smart contract that re-executes all of the transactions would effectively be an extension block protocol. So again, we have the rollup node. The rollup node is going to scan Bitcoin blocks for transactions that look like rollup transactions. And it's going to pull these transactions out and just execute them one by one according to the consensus rules of the rollup. And if the block turns out to be valid, then it's going to add it to its local blockchain. And then it does this for the next block, and it'll add the next block to its chain, and the next block, and so on, ad infinitum. Those are re-execution rollups. And we also have validity or ZK rollups. And in validity or ZK rollups, rollup nodes will verify a cryptographic validity proof, which proves the validity of the rollup state transition. The rollup transaction data can be compressed and stripped down to just the state diffs to minimize the data availability costs and maximize transaction throughput. So in this model, with each rollup state transition, we have not only the rollup state data going into the smart contract or into the Bitcoin block, but we also have this validity proof. And so what the rollup nodes can now do is, instead of re-executing every single rollup transaction to find out what the current canonical state of the rollup is, instead what it does is it scans the Bitcoin blockchain, looks for these rollup state transitions, pulls out the proof, makes sure that the proof is valid, and if the proof is valid, then it just takes the data blob of the rollup state diffs and it applies the state diffs to get the new canonical state, and then it does this sequentially for each block after that, again ad infinitum. So to recap, with the different kinds of rollups that we have are sovereign rollups and smart contract rollups. And then the most common kinds of smart contract rollups that you're going to hear about are optimistic rollups and validity or ZK rollups. You can also have optimistic or validity sovereign rollups, but you'll probably hear more about the smart contract variety. So why do we even care about rollups? Why are people working on these things? So one thing is that rollups can make Bitcoin more scalable, supporting up to 250,000 transactions per block versus around 7,000 transactions per block today. I broke down the math on this in a paper that I published a couple of years ago, which is at bitcoinrollups.org, comparing the throughput that is enabled by different kinds of rollups compared to just doing a normal, one input, two output, pay to witness pub key hash transaction on the Bitcoin main chain today. And these are the numbers that came out the other side of that math. This is actually a relatively conservative estimate. I think you could probably get more, at least maybe 50% more, 25 to 50% more transactions, but yeah, someone's got to actually go and do it. Another benefit is that this is complementary to existing scaling protocols such as Lightning. So you could imagine that these transactions per block are not just on-chain Bitcoin payments, but these could be like Lightning-related transactions, such as channel open, channel close, channel rebalancing, all of the different kinds of channel management transactions that somebody would do in Lightning. So it makes Lightning itself more scalable by just enabling more of the kinds of on-chain transactions that users would normally have to do. Rollups can also make Bitcoin more programmable. For example, we could experiment with new kinds of smart contract languages and applications without having to make any further changes to Bitcoin layer 1, such as new self-custody protocols like vaults or account abstraction, new collective custody models like smart organizations or DAOs, new peer-to-peer financial transactions such as pooled borrowing and lending, new security, UX, and throughput trade-offs like validity chains, coin pools, ARCs, etc. So this is a screenshot of an application that was built on Rootstock, which is an EVM-compatible Bitcoin sidechain. We could imagine this same kind of application being deployed to an EVM rollup, where we get this new capability, which is a spending limit. This is basically says, it applies some logic to your account that says, you're only allowed to spend so many Bitcoin within a given period of time. And then your allowance is kind of reset after that period of time. They can also make Bitcoin more private. So with rollups, we can adopt state-of-the-art privacy technology without affecting layer 1 transparency and auditability. For example, we can add optional end-to-end encryption for Bitcoin transactions, giving us near-perfect privacy, encrypting the sender address, the recipient address, the transaction asset, and amount. For example, there was a rollup built on Ethereum called Aztec, which implemented this kind of shielded end-to-end encryption protocol where the only data that you see on chain is just the zero-knowledge proof and ciphertext, which provides a very high degree of privacy compared to normal Bitcoin transactions. So what are the options for actually building a Bitcoin rollup today? One option is the sovereign rollups that I mentioned earlier. These are relatively easy to build, but there is no trust minimized BTC bridge. That is one of the defining features because the sovereign rollups don't have any external dependencies. That includes not having a smart contract that defines its consensus rules. And so you have to use a less than trustless bridge, like a federation or custodial, some other kind of custodial bridge. And you can think of embedded consensus protocols like Omni, Counterparty, or Blockstack, et cetera, as early iterations of this concept. The main difference being that instead of having a dedicated block producer who aggregates the transactions and then puts them into a single Bitcoin transaction to get them confirmed, in these protocols, users were just putting their transactions directly onto Bitcoin. And then there was this separate full node software that was reading Bitcoin blocks and interpreting the Bitcoin transactions as being related to their protocol. But it's a conceptually very similar concept. Now, smart contract rollups are more difficult to build, but they provide users with a trust-minimized BTC bridge. All of the rollup bridge variants today require some kind of trusted setup. But if we have a soft fork to enable native direct validity or ZK proof verification, this would enable like true L2 trustless rollups. So you could bridge BTC back and forth without having additional trust assumptions. So these are some of the varieties of smart contract rollup bridges that are possible today. We have the BitVM2 bridge, which gives us one of n we need one of n trusted third parties for liveness. And here liveness refers to being able to actually process withdrawals from the bridge. We need at least a single altruistic user for safety, that is to prevent the bridge operators from absconding with the user's Bitcoin. And they do support custom logic. So you can, once you actually have the BitVM2 bridge set up, if you can build the bridge program in such a way that you can have pretty much any kind of blockchain or protocol sitting on top of that. There was the rollup that was introduced by Barak. In this protocol, there is no trusted third party required for liveness because users can always unilaterally exit back on chain. But you do have this one of n trust assumption for safety. So you require at least one of n parties to be honest to prevent theft from the bridge. And it doesn't support custom logic. There are only a limited number of applications that rollups can support. And then finally, there has been this recent paper about pipes, which is based on technology called functional encryption. This is still theoretical at this point, but if we take the assumptions in the paper at face value, then we can say that it is actually trustless for liveness because users can basically exit from the bridge themselves. But they still rely on this one of n trusted setup for safety to prevent theft from the bridge. And the good thing about them is that they do, one of the other good things about them is that they also support custom logic. So once you have this program set up, you can have any kind of blockchain or protocol on the other side of this bridge. Now, if we look at some of the bridge designs that have been proposed that require a soft fork, one is MAT. This would be useful for optimistic smart contract rollups. In this case, they also have a trustless liveness guarantees because users can unilaterally exit from the bridge. They rely on a single functional user, just somebody out there on the internet who has Bitcoin and is watching the protocol to ensure safety in case somebody tries to make an invalid withdrawal from the bridge. And MAT-based bridges also support custom logic. So you can have any kind of program that is secured by a MAT-based bridge. And then there is the GSR class of smart contract rollup bridges, that is the great script restoration, which brings back a bunch of old opcodes that were disabled by Satoshi. With this suite of opcodes, we can also get trustless liveness guarantees from the bridge, as well as trustless safety guarantees, because we'll be able to do native validity proof verification in Bitcoin script. And this kind of bridge also supports custom logic. So you can put any kind of chain or program on the other side of this bridge. But as I mentioned, these last two variants do require a soft fork. So there are some known concerns when you're building or maybe using a rollup on Bitcoin or any other chain for that matter. You have to worry about faulty bridge operators. Depending on the style of bridge, the attack vectors differ, but in all of the bridges that I've discussed so far, other than the trustless smart contract ones, you have to worry about some kind of operator collusion. If enough operators collude, then they could steal from the bridge, possibly, again, depending on the design. Some of the prover systems in the ZK or validity proof-based rollups require a trusted setup. Not all proof systems require trusted setups, but some of them do. And usually you have a one of n trust assumption there. If all of the trusted setup participants colluded or somehow failed to delete their toxic waste, then this would enable proofs to be counterfeit and That's bad. Deep reorgs might be a concern, particularly for the challenge and response game. In the optimistic rollups, again, in the optimistic style rollups, challenge transaction withholding is a concern, and this is primarily like if there is an attempt to make an invalid withdrawal from the bridge, and there's some user out there who wants to challenge that. They try to put their challenge transaction in a block. Well, what if the Bitcoin miners just ignore that transaction? What if a hash power majority coalition are the ones who are actually trying to make the invalid withdrawal, or they're colluding with the person who's trying to make the invalid withdrawal? Then they ignore the transaction for the entire challenge period, and the invalid withdrawal is actually able to go through. That's a concern. Rollup transaction withholding. So if you send your rollup transaction to the rollup block producer and they just ignore your transaction, what are you going to do? High confirmation latency. So some rollup designs will put every rollup onto Bitcoin as soon as possible. And so you have, in that case, you have a minimum latency of about 10 minutes. But other designs, they do batches less periodically, maybe once an hour, maybe a couple times a day, just because of how expensive maybe the proving process is. And so you could have the even higher latencies, confirmation latencies, if you're waiting for that final Bitcoin confirmation. And if you try to get around that by just trusting the rollup block producer, they tell you, oh, I'm going to put your transaction in a block, it'll go on chain, I promise. How are you actually going to secure that promise? And finally, if you have multiple of these rollups set up on Bitcoin, how are they going to interoperate with each other? If a user is on rollup A, wants to pay a user on rollup B, or use a smart contract on rollup C, how are they going to do that in a way that is secure and perhaps relatively low latency, relatively good UX? These are all concerns. Some of them have known solutions. Some of them don't. In other cases, we have mitigations, but not necessarily bulletproof solutions. These would all be topics for maybe a Bitcoin Rollups 201 talk to go deeper into the rollup design space. But that summarizes the Bitcoin Rollups 101 presentation. And so I'll be happy to use the rest of the time to answer any questions, go back and review any of the slides. Thank you for listening.
All right, right back there. First question.
Hi, great presentation, by the way. My question is, how do you think we make rollups interoperable? Do you think we need like an ag layer or a sequencing ag layer, or like an intent bridge that just has liquidity on all rollups? Like, what do you think is the best solution to bring interoperability with all these rollups?
I think it depends in part on the use case for interoperability. Like if it's a payment, then you might get away with something like an intent-based bridge. Maybe even you could like make this trustless with atomic swaps or something like that, and make it relatively good UX. For other kinds of transactions, like smart contract calls or like cross-chain voting or things like that, then intent-based bridges might also work, but an atomic swap might not be the best solution there. Rather, it would be some other kind of account abstraction-based, intent-based bridge message passing thing. I think because of Bitcoin's relatively high latency, you've got these 10-minute block times. Even if you have like an ag layer kind of thing, you would still need to have some kind of additional like faster confirmation mechanism that's maybe like crypto economically secured with a slashable bond or something like that. And so I think maybe an ag layer kind of thing is part of the one piece of the puzzle, but it's not like the only part of the puzzle. But yeah, it depends in part on the actual use case for the interoperability, and we'll have to wait and see how the market actually ends up like solving these problems. All right, I'm gonna call it. Thank you guys.
You have seen the